Hello, everyone. So, welcome to our fourth webinar in a row. So we are doing it. We're becoming creating a kind of cultural thing. This webinar. So, well, welcome everyone. Today we are celebrating our fourth webinar, having an in-person meeting.
Yes.
So, hi Ellie, hi Emmy. How are you doing?
All fine here, Chema. Finally, we are meeting here.
So we are in Madrid, actually. So you can see that it's in the afternoon here. So good morning for the people in America. Good night for the people in India. And yeah, so what do you have today?
I wanted to ask you, this week is the Engineers Week globally. So congratulations to all engineers. I mean, everybody except me and I in this webinar. Uh,
Yes, I know.
It's an engineer education.
ah,
I understand a couple of things, but
okay.
well, in my beginnings, I broke many things. I want to discover how the things were built, so I tried to probe, and this was the reason that I like engineering. Did you broke anything?
Um, my specialty is testing materials.
Oh.
I used to broke a lot of marks when I was a child, so
Oh,
yeah.
that's a fun. And you, Chema?
Well, I'm planning to break things today. I mean, I used to break a lot of things, especially uh, break and lose things. So I'm very easy with that. I'm breaking.
Sorry for the interruption, but I need to ask, when we talk about break, are we talking about break something? Because I know this is a transformer. I mean, maybe you can show, this is the transformer, and today we are be talking about.
Okay, I was planning to break Frenetic simulator, but also we can break we can break the laptop. So we can do something. If the Frenetic simulator didn't broke, we break the laptop.
Okay.
Okay, let's say.
That's it.
Let's say we have a very robust tool. So
We'll see. We'll see.
okay.
Actually, I think that this is the fourth webinar, and we have had some, let's say, some problems some days, but we haven't really broken the anything big. And today I was preparing like, okay, we're going to talk about LLC converters, and I need to be honest, I'm not an expert in LLC, so be ready for breaking something today.
So maybe you have to use the hammer.
Yeah, I would use it. I would use it. Um, let's keep the hammer here. So should we start the
Yes,
real
we're
webinar?
gonna.
Okay.
We have many people there. Thank you for being there. And I'm meeting. Well, we are not today, so we can start with the LLC.
Okay, so let's start. Let's change the micro or no? Yeah.
I think the sound is good.
Okay, so let's use here. So I'm going to share my screen. Okay, this is the typical webinar presentation. Now it's becoming a classic. So what we're going to do today is to talk about LLC converters. But before, let me go through the simple agenda. Actually, there is a mistake already in the agenda of the generative planar magnetic. This is from the last week. So first thing, let me remind you that what Frenetic is a company that have created the best simulator for magnetics in the world. And just for you to know what you can do with this technology, we have created some use cases, and this QR code can be used for getting a free demo of our technology with one of our experts. So some of the cases here is like we have customers that they have shared with us some use cases. So some of them could be like creating a very complex CLLC transformer. And even if you don't have any idea about this converter, don't worry, because with our technology, we'll be able to generate all the way from some everything needed to just design this transformer. but maybe you already have a design. So this is the case too, where you can simulate an inductor that you already have. There are other cases where you can go to extreme conditions, like a high temperature or high voltage isolation, where you can go to our SIDS case, where typical application for oil and gas, or somebody that is suffering from a hammer, So, if you want to get more information, please request a demo for us. But now let's talk about our vision for Frenetic AI. So what we are trying to build here is a technology that allows engineers to work in the whole process of designing a power supply. So most companies or more engineers, they are working from standard specific, let's say, electrical specifications, even mechanical specifications, until the lab test. So we cannot go with them to the lab, but we can try to work with them in all the daily tasks that they can have, not just designing tasks, but also tasks for work, let's say, review schematics, mechanical design, PCB layout. There are a lot of tasks that we are trying to develop new tools that allows the engineers to have a kind of AI companion for the daily activities. And today, I'm going to talk about LLC, but I mean, and every engineer usually learn one or two topologies during their academic life, and then maybe another two topologies during their work life. And my case is that I'm not an expert in LLC at all. And actually, we have made two previous webinars, one by our friend Lucas Niteza, the one by Nicola Rosano, about LLC design using our technology. And we will share with all of you the links for these webinars that are excellent webinars where you can learn how to make the design of the resonance and all the details for this kind of technology or this kind of topology. Because I'm not the expert. So you will say like, hey, if you are not the expert, so what are you going to do today? It's like, actually, that's the reason that I'm going to talk about the LLC design for the converter and for the transformer, is because I'm going to use technology that will allow me to work with this topology without being a real expert in this LLC design. But again, we will share these videos and this material with you later, where there is like a very detailed explanation of all the equations. So let's go to the platform to see how we're going to proceed. I'm going to start talking about a specific specifications from Infinium for this case. So I'm going to take this application node from Sam Abdel Rahman. It's an LLC full bridge of 250 watts, 33 volts input, 400 volts output. So in this document, they explain the whole process of how this converter is working, how to calculate the resonant values, the inductance, the resonant inductance, the Q, all the parameters that need to work for the operation. And what I'm going to do here is to see that there are these design steps. I'm going to check these inputs for the specifications. So okay, let's go. Here we have. So the input is 400 volts output actually. And this input voltage range, 250 volts in the power. We can see here that for the range, when you're in the lower value, 18 volts in the input, you only can deliver 125 watts in the output. So this is going to be interesting for today. So now what I'm going to do is take these inputs and come to our plan for the design of the LLC. I'm going to write the input, say 53 volts, the output 400, and the power 250 watts. I'm going to choose full bridge LLC, and let's see if we are going to break something. So this will take 1 or 2 minutes because we are trying to follow like a real time demonstrations. So I said before, today I want to break something. And let's see if we are able to break or it's going to be easy to break. So while we're waiting, are you experts in LLC? I have no idea.
I have tested some, but well, following Frenetic rules.
Okay, so I have been very familiar with full bridge phase shift my whole professional career, and at the beginning, the three phase duality bridge. Hey, there's something working here. Okay, so we can see that the system proposed a switching frequency on 100, same thing that resonant frequency, 100 kilohertz, tune radio 0.0825, magnetizing inductance 14, resonant value 2.8, and these are just the values of the current input and output. So since I know that this will take time as well, before checking these values with the application note from Infineon, let me generate the LTSpice file. So these are 14 microhenries for the magnetizing inductance, 2.8 for the resonant. So let's see what Infineon proposed. Well, I can see now here, the tune radio 0.085, so it's actually exactly the same. And here also we can see that the resonant frequency they choose is 110. So in our case, it's 100, so close. Leakage inductance is 2.2. In our case, is 2.8. And magnetizing is 14 in our case. They propose 12. So it's pretty close. So even if I have no idea how these values were calculated, I can get this information. So let's come back here to see what's happened. So okay, the file is already here. So I'm going to download, and now I'm going to open LTSpice to open the schematic. That's I just download here. So actually, it's this one. So and simulate. So now we have a simulation for this LTSpice for this particular case. Let me do some zoom just to make sure that I opened the right one, because I think that was like a. So here we can see the values of the resonance. Yeah, the resonant inductance, tune radio, and the magnetizing inductance. And this is an ideal simulation. This is usually a question that we are receiving lately. Is like, is this an ideal simulation? Yes. We're working to include models for the switches that you can actually decide, okay, which switch do you want to include? And also we are working to make sure that you can update the transformer with the details of the transformer design we are going to do. Actually, I'm going to ask the system to design a transformer in the meantime. So this is going to run a design transformer. Let me come back to the simulation. So here, this is almost everything is ideal. So the waveframes are very nice, and there is no, sorry, there are no kind of spikes. And actually, even here, I can see that the voltage is still growing. So we will need to check if this is good. So there are just pretty few grow, but this will need to be checked if there is an oscillation or what. But the circuit is ideal. And one of the good things about doing the design of the magnetic now, okay, there we go, we have here the design, is that we can update the simulation with all the parasitic of the magnetic. So to do that, I'm going to open the simulation of this magnetic in detail. So I'm going to store this design. Now I'm going to open the simulator. So let me open this one. Okay, this is the one for now. So what you can see is that this is the full virtual LLC, the same one that I have been designing here. Actually, let me put these together. So we have, this is going to be a E25 suggestion for having two chambers. So I'm coming here and let me check if it's the same. So E25, that's correct. And here we have this winding. So, so the most interesting thing about this topology and this design is that most people want to work, want to create a transformer and an inductor together to have in this topology just one single magnetic. So instead of having two magnetics for this topology, you can have one single component. So you will be saving one of those and saving money, also space, losses, everything. So for doing that, we need to design this transformer, ensuring that the leakage inductance has the same value that the resonant inductance, in this case 2.8. So this algorithm has created this transformer, and now we're going to check if this is true or not. So we check here secondary, and there we go. The resonant, let's say the leakage inductance in this case is 3 microhenries. And this value actually is going to be the one that we will need to update for the resonant, because instead of 2.8, this one is 3. And the nice thing about this value is that, okay, but how can we trust this value of 3 microhenries? So what we have is we have made an analysis with our, let's say, with this model, going to the lab. So we have an analysis of this model. We went to the lab, we made them, let's say, this is an article explaining the details of the model, and then we went through the rectification process and getting this, let's say, the value of 95% of accuracy over these measurements, well, in average. So we can say, like, we are very confident of this value of leakage inductance for this case. And now I'm going to test something. It's like, if you remember, I made this design specs. It's not 33 volts in the input. It's from 18 to 36. So now I'm going to test what's happened. What's happened if I test these under a different operating conditions, let's say 18 volts. So, oh, I told you, I'm going to break something today. So what is happening here? What is happening? Well, what is happening is that we haven't done the design for the right turn ratio, for the right values, because during the design phase, we only include just one nominal value. So we need to come here again and write the whole range. Oh, I forgot this, the whole range, to make the simulate the run again, to get the design and get the new turn ratio that this really will help us to have, let's say, to allow the converter to work in the whole range. And actually, just not only in the whole range, is that at this input voltage, we have learned that only can reach half power. So we can update that. And now it's working. I can simulate this one, and even I can just create a couple of operating conditions like this one and this one, different points, let's say 36 and I don't know, 250 baht. Is working, yeah. And try to have a report for all the cases to compare like different designs or different operating conditions. So as you can see here in this table, we can see that we have the different turn ratio. And you will ask me, hey, what's happened when you are doing a design? You know that for different power levels, you need a different switching frequency, let's say Yeah, you are controlling the LLC with a different switching frequency. That's correct, and this is something that that in this point we are just working in, let's say, with input voltage range and one value. So if you want to know exactly that maybe for this value, how it's going to be the resonant frequency, let's say the switching frequency, Frenetic takes automatically the value needed. So here you don't need to know which is the switching frequency for each power level. Just writing the resonant frequency, this is taking the calculations. I think that's all from my side. I'm for the, let's say, for this part of the demonstration, but I want to remind you that now every week we are having this 20 minutes or 30 minutes webinar. So if you want to come next week, we are going to talk about zero voltage switching in full bridge phase shift. This is the only one that I know, so that's gonna be more interesting for the audience. And it's gonna be next week, more or less similar time. You will receive let's say the registration code, but if you want to take the advantage now to use this QR code, is totally fine. So that's all. So I'm going to stop sharing, and now we still have 5 minutes for questions.
Yes. Before the questions, when you're reading, just to comment that all the people that is registered for this webinar, we have sent you the credentials so you can access to the tool and test. You can test with input, you can test with range, and also as Chema shows, you have a box that you can put some constraint dimensions or whatever in order to have more accurate designs. Remember that you need to wait a bit and open just one tab. All in order to thank all the people that has joined our series of webinar, we have extended this version so you can continue testing, and then the idea is that you can get most of this value and share your feedback with us. And so we have extended all the license, so you can experience this tool many days more. We have a couple of questions.
I think that the first one is about if is that a step down transformer. Actually, it's a step up because we are from 33 volts to 400 volts. More questions.
Yes, I have another question here. If we are including half bridge also, yes, it's something that we are planning to include. We are spreading different use cases and also different topologies every week after week.
Actually, I don't see exactly the same questions here. So, there is another question about the
Planners.
The planners. So yes, actually, a couple of weeks ago, we made the demonstration of planners. It would be ready for everyone to be used at, let's say, very soon. And actually, we are playing right now even to include just not the planners in PCB, but other technologies in planner. So yes. I think that somebody asked for what means the integration between the liquid inductor and the transformer to save space. So let me go a little bit more in detail with that. So when you have a converter, like let me share my screen again.
There is another comment for the same person. I mean, the external leakage inductor.
Well, it's the same. So let me share my screen again. So maybe I have here a picture of the converter. Yeah, this one, or we can use our picture here. So when you're designing a resonant LLC, you have a resonant tank, usually with a capacitor and an inductor, and this inductor that is going to be used for the resonant can be an external inductor or can be the internal inductor of the transformer that is the leakage inductance, is a parasitic. So when I'm saying that you can integrate both, is that you can use the leakage inductance as the resonant one, and then you don't need to add an external inductor. So finally, you are using the transformer as a transformer and resonant inductor at the same time. So let's another question.
The model to calculate our losses.
Sorry?
We have one regarding the model to calculate our magnetic losses.
Yeah. So the losses that we are calculating is like the core losses, the winding losses using a 2D model. It's not double, so it's a little bit more complicated, or let's say quite more complicated. And in the winding losses, we are considering skin effect, proximity effect, and yeah, and all this part. Let's have the last question because we are already almost out of time.
Yeah, we have, if we are, well, we are going to provide the PSP Altium for the planners.
PSP Altium, the
project, yes.
yeah, I mean, something that we are working is in the footprints, for the transformers for Altium. So if this is something that we see the more interest and interest is growing, we will accelerate that in our priorities. But is the generation of these footprints for Altium is one of our, let's say, challenge that we are facing right now and is in our roadmap.
Yes, great. Right, there are a couple of some more, and we are going to reply that after maybe by email. Well, I think that we are running out of time. So
Yeah, but again, thank you very much for attending these webinars. We are very excited that this is the 4th webinar in a row. So we will keep doing this as soon as you are coming. So thank you very much. Next week is going to be a little bit more theoretical because we will talk about zero voltage switching. So I hope that you come next week and yeah, enjoy the platform and enjoy testing Frenetic AI, the ones that have access.
yes.
Do you want to say something?
Yes, thank you a lot for being here. We are building this together, and the idea is that we can help you in your magnetic journey. So keep being here with us, and we are going to build something great.
Okay.
Thank you.
Bye bye.
Thank you.
Thank you.